Hi, students. Okay, we're at the 4th chapter now. Can you believe it? So, in the 4th chapter, we're going to look at something called measures of variability. And this starts to answer questions like, in a distribution, how far apart are the scores from one another? Well, your first thought into this may be, oh, well, I know, I can look into the range. So, let me give you an example. In one of my classes last term, I had one person scored 0%, and then another person at the top scoring somewhere, let's say 92.5%. So there were 34 students in the class. So if there was one student that had 0, didn't really do that much, and another student scored 92.5, something like this, then we're still left with 32 other students that are in this range. Without any further information, if all I told you is, well, the range is 92.5%, from 92.5 to 0, max to min. So this is the max score and this is the minimum score. So what you would know is, well, I know the range, and if I didn't tell you what the max and the minimum is, you just know one piece of information, and that is how far apart the scores are between the maximum score and the minimum score. And you wouldn't know anything else for the other students, or in fact, all of the students, if that's all you're told, the range. So in that sense, we need better measures of variability. Just like in the last chapter, we had different measures for central tendency to answer questions about the expected value. Now we're going to answer questions about spread. That is how wide the distribution is, how far the scores spread apart. Not just between the maximum and the minimum, but also how far they are apart from each other. Now, you could rank the scores, from lowest to highest and, measure the differences between them, but then you'll be just getting distances between pairs of scores, and how you order them would change these differences too. So we need a consistent way of, finding out how far the scores are apart from one another. For example, if I got 5 numbers, 1, 2, 3, 4, 5. And so, yeah, I can tell you the range. The range is, 5 minus 1, that's 4. Yeah, great. So I can just tell you, well, the range is 4. And you might want to know more. So maybe you want to look at how far the scores are apart from one another. Well, I could go 1 and 2. Okay, cool. So then that's 2 minus 1. That's 1. And you could do this for each pair. You rank them, and yeah, you can say, oh, well, if I rank them from smallest to largest, each person in this particular distribution, the scores would be, 1 apart from one another. But what if I happen to forget to arrange them and start mixing up the order? Something like this. Then 1 and 5 would have a difference of 4, 5 and 2 would have a difference of 3, and you would end up using the numbers more than once too. So we need a consistent way, some way to figure out how we can get an expected spread to answer questions like how far apart the scores are from one another. And to do this, we're going to need the number that is calculated by using the mean. And this number is going to be key. So as we learned, the mean is one of the measures of central tendency that's mathematically derived. That is, you need all the numbers, all the scores, and then you divide it by the number of scores. And this is the value that we're going to use as a reference point rather than the maximum and the minimum, with which we measure each individual score, each raw score, with the mean. So this is going to be the foundation of our measure of central tendency. And so this chapter is going to talk about this. And this would be a short intro of why we measure variability in distributions. So in terms of learning outcomes, there are 6 in this chapter. I'm not going to talk about how long I'm going to make this video or aim to anymore. I'm just going to do it. I would expect somewhere in the range of 2 hours. But again, I'll split this into 2 parts. And so the first part will cover the first 3 outcomes. Number 1, we would describe the purpose of measuring variability. 2, we would define the range of the frequency distribution. We talked about this as well as its limitations in the introduction already, but we'll go into a bit in depth. Number 3, we will compute the range of the frequency distribution. Pretty simple so far, right? 4, we start looking at something else called the variance and the standard deviation, a more consistent and reliable way of measuring variability in a distribution. Again, here, just in case, an easier word for variability would be spread. So, for example, a distribution like this is thinner, it has less spread than a distribution that is like that. You may think here, flatten the curve. Hashtag, I guess, the curve. In light of COVID-19, which is around the time we recorded this, when this is happening, or what is what we're trying to do to ease the burden on the hospital workers and healthcare workers, which is often called the front line in an epidemic like this, is so that the hospitals don't deal with so many patients at once. And so the deaths would occur for longer, but the hospitals don't have to deal with so many at once, so it's more quote-unquote manageable. But again, this also deals with the measure of spread. The spread here is the time. So for a large spread, it would be fat and probably flat, whereas a thin spread would probably be thin and tall. Okay, and one of the ways we can consistently measure this, again, back on topic, and the learning outcome is variance and standard deviation. Number 5, we're going to look at the components of this, starting with the sum of squares, and we're going to talk about why we need the sum of squares instead of just using deviation scores, which we get the variance, which is another way of saying the expected deviance score value, and then the standard deviation, which we'll talk about why that is once we know, we're working with sums of squares. And finally, we're going to do this 2 times. In the 5th learning outcome, we're going to do this for population frequency distributions. And for number 6, we're going to do this for sample frequency distributions. Now, there is a major distinction between population and sample, especially when we calculate variance. As a heads up, population will use n because we're getting everybody, and sample, to account for sample bias or sampling error, we use sample size minus 1, which is another way of saying degrees of freedom. And we'll talk about this as well. So these are our 6 learning outcomes, and we'll cover at least the first 3 in this first part here. The math tools you're going to need, you can probably guess some of these. Because we need to do averages, we need to add up the scores, we need sigma notation, we need algebra and basic math, so order of operations is key. The mean is measured already, and as a review, you probably want the median as well. But the key here is the mean. Again, another way of saying standard deviation is like the expected deviance score, which is like the average deviation score. But there are steps to get there, and we're going to talk about that. So variability overview. As we go through the chapters, as we progress in them, as our knowledge and skills in statistical procedures grow, in both knowledge, concept, skills, and practice, the overviews can be shorter, starting with this one. So as we've already introduced variability, then here are what the points said. It's a quantitative distance measure. we are measuring distance between scores. So a more formal way of saying it, yeah, quantitative deals with numbers. I'll just write actual numbers here because we're measuring them. Difference between scores. Done. It also describes the distance of the spread of scores between a score and the mean. So remember what we talked about. In the first point, if we try to find the distance between scores, there are multiple ways of doing it, and it's hard to get a consistent way. One consistent way is the range. There is a maximum and a minimum, and you can get that every time. But the scores in between, you can jumble them up. Another way that is consistent as a point of reference would be the mean. If you know every score in the distribution, you can calculate the mean, and you should. And so using the mean, we can use that as a reference point to figure out what each score is in relation to the mean, and we measure that by the distance between them. That is the score and the mean. And we want to measure variability in the distribution because we want to do more accurate descriptions of the distribution. If we only know the expected value, you only know one value. However, if you know the variability, if you know the spread of the distribution along with the mean, not only do you know the middle point that you expect, but you start to know how far the other participants, for example, if you were in a class and you knew the class average, that tells you what you would expect, but it doesn't tell you how the other people really did. Some, again, could score better, and some would score not as good, or not as well, I should say. And so the variability or measure of variability would tell you such things. Another way of looking at this is your letter grades. Your letter grades are actually measures of variability. If C was the average, which it often tends to be, B and A would be measures of variability, and they're actually technically standard deviations away from the average above, and D's and E's, if there is an E, but F's would be standard deviations below. So it would look something like this. Again, a bell curve would be a common example here. So you would, C would be kind of the average performance, and then students who score better or worse would be further away from the mean, and you would expect fewer and fewer people to get more extreme scores. And we can again measure this using measures of variability, sum of squares, variance, and standard deviation. Again, the range can only tell you the minimum and maximum. It cannot tell you anything else besides that. And using standard deviation, it can tell you stuff in between the max and minimum. There are other ways too, like interquartile range and box plots, but in this chapter we're going to talk specifically about standard deviation derived from variance, which is derived from sum of squares. So let's take a look. Here's a simple picture of variability, and I've already talked about this in the beginning. And here is one that is thin and tall, even though these are the same height, and there's no y-axis per se. We don't really need the y-axis in this case. We're just looking at the width, so how wide it is on the x-axis. This one is definitely quote-unquote thinner, has less of a spread even in numerical value. If you just look at the range, it is 82 minus 58, which is 24. And this one has a much larger range, and this is pounds. This is quote-unquote fatter, the curve, wider. And the range here is 230 minus 110, so that's 120 pounds. It's good to say the units as well. So the first one, the thinner one, is in distribution A, 24 inches. And the range in this guy, B, would be 120 pounds. Again, with the range, we only looked at 2 points, the maximum and the minimum. In these distributions, since, if you remember, it's symmetrical and one mode, so the mean, median, mode are the same, we're going to use the mean as well. In distribution A, that would be 70 inches. And in distribution B, that would be 170 pounds. And noting that there are scores underneath the curves in these distributions, we can start measuring how far the scores are apart from each other by measuring how far apart each score is from the mean. And we're going to get into that as well. So the mean is going to be our reference point. So again, there are 3 measures of variability. By this point, we would have discussed already a number of times the advantages and limitations to each one. And so here are the 3 in summary. The first is the range. Again, that's the maximum minus the minimum. Okay, and we talked about its advantages and disadvantages. Advantage, it's pretty easy to do. You just need to know 2 scores, maximum and minimum. But the disadvantage is, again, you only know the difference between those 2 scores and you don't really know anything else, especially if they don't tell you what the maximum and minimum is, but they should. Variance is the first step to get a more consistent measure of variability, which we'll be using in other chapters as well, like getting z-scores and using that to calculate standard error in hypothesis testing and so on. The standard deviation is the square root of the variance, and we'll talk more about that. So they are, and when I say they, that is the variance and standard deviation, they are closely related. Again, the standard deviation is the square root of the variance, and they both deal with the expected deviation score based on how far the scores are apart from the mean. So first, let's start with the range. If you already know what the range is, these points are pretty straightforward, especially if you were listening to this from the beginning. You'll probably get these points fairly quickly. So let's jump right through them. It's the distance covered by the scores from smallest to largest. That's done. We talked about this. For continuous data, we use, and this is a fine note here, real limits to find the range. Again, logically, the max value would have the upper real limit to get the maximum value, and then the minimum value, we use the lower real limit to get the smallest value possible. So for example, if this was the minimum, and let's say if it was 1, then and the lowest value is 0, then the lower real limit would be 0.5. Let's say here was 99 for the maximum value, and so the upper real limit would be 99.5. And if those were actual scores right here, your maximum and minimum, the range would be 1 more than the apparent range. When we're dealing with continuous data, it would be 99.5 minus 0.5, and that would be 99, instead of 99 minus 1, which would be 98. So again, when you hear continuous data, pay attention to real limits and make sure you use that. And make sure you know, okay, for real limits, I have to know the interval size, or the size of the interval between each point in the x-axis, and then half that distance would give us our upper and lower limits depending on the direction. Upper towards the positive direction, lower in the negative direction. Again, disadvantage, it's based on only 2 scores, the maximum and the minimum. It does not include the remaining scores, yet another disadvantage. Therefore, it is an imprecise and unreliable way of measuring variability. So while it is the easiest, it is also probably the least reliable of the 3. So we need something better. Which leads to standard deviation and variance. And one of the more straightforward ways of explaining this without using formulas, and I'm going to take a break from talking for a moment. If you just want to know where the formula sheets are, yes, you can find it too in our course at Alexander College. You can go to the modules, which is here, and go down to your statistics resources and go to summary of statistics formulas page 1, which would take you to this page. You can download the sheet if you want, or click this button, which would give you the download. and I enlarged it already. And so in our previous chapter, we covered the mean. Yes, we have formulas for the median as well, trying to locate the middle score, whether that is for an even sample size, an odd sample size, or for continuous variable, which we need the precise median, figuring out the fraction in the interval. And you can go back to either your textbook or the video to review if you need it. And it's a good idea to review anyway and practice. In this chapter, we're covering these three in terms of formulas. Now, if you can translate these formulas, or rather these values and the operations that is involved, operations that are involved to derive these values, then yeah, looking at just the formula sheet can get you started and you can understand it pretty well. However, our approach to it, to getting us to look at the definitional and computational formulas for sum of squares, there is a mathematical proof for this, which you can ask me directly, and the time does not allow me to cover it in this video. There are two ways to find it. One, you can derive it yourself. If your algebra is strong, or you feel confident about your algebra, give it a try. It's a good idea. You can see it for yourself. Or you can start Googling it and look for various types of proofs. Some are easier to read than others too. So again, it is strongly recommended if you really, really want to know why there is a computational formula for the sum of squares. Try it and see. Again, the base, the home base, so to speak, your foundation for the sum of squares is the definition. If you can explain how you get the sum of squares and why you can do it, and why you square these deviation scores, raw score minus the mean, and you add those up, which once you get it, it'll be really simple, and that's good. If it feels like that, that's great. Your understanding in statistics is getting stronger. Once you get that, and you can see, oh, okay, computational does help me get it faster. But again, the definition is what I go back to, which you'll use for variance. And you can see here the sum of squares divided by n. That kind of looks like your average, doesn't it? You added up all your x scores, and then you divide it by the total number of participants in either the sample or the population. So just like the mean is the expected score, the variance is the expected sum of squares, so to speak. And because we squared the deviation scores, your standard deviation then looks at the value as not sum of squares, but square root of the sum of squares, which goes back to our deviation scores, which is derived from the idea that an absolute value of something is the square of something, and then you square root it again, which cancels out any positive or negative, signs. Specifically canceling out negative signs. And we'll talk about that, why we do that as well. Again, variance and standard deviation are expected deviance scores. And this is the formula to do it. And we kind of went over the story a little bit. But for our lecture's sake and for our story's sake, we'll go over it in the slides. So there you go. That's where you can find the formulas. And those three, sum of squares, variance, and standard deviation, are the ones we're going to be using for this chapter. So here we go. In terms of measuring variability, the standard deviation, which is used quite a lot in teaching and in statistics, we want to know the spread. And as far as we know, the standard deviation is indeed the most common and important measure of variability. As the outline or the points say, it gives us a standard or average distance between the scores and the mean. And we use the mean here as a reference point. And we should, because the mean is a measure of central tendency. And when we know all the scores, as we should, or at least ideally, as often as possible, it is a good measure of central tendency. And it will give us a good reference rather than just maximum and minimum or any other score. It also tells us whether the scores are closely clustered together around the mean or they're widely scattered. Again, using the mean as a reference point and not just a balance point, as we talked about in the previous chapter of the distribution, then we can clearly say whether a distribution is widely spread or close together once we calculate how far the scores are apart from the mean. If you're feeling at this point I'm being repetitive, yeah, good. If you feel that, that's good. That means you're understanding it. If you are still struggling, that's okay. Again, you can think about this in terms of, oh, okay, how far apart are the scores from something? How do I tell? I got the range, which I know how to do. Now I need to find a reference point. And you can pick any central tendency measure if you were thinking about chapter 3, for example, if we're following along in the course, and the mean would be the best to go. The variance is necessary as a companion concept, is the precursor concept, the one before it, because we need to cancel out the negative values in our deviation scores, and the way to do that is to square the deviation scores. One final note here, and this is point 3, or bullet point 3 here, is that for population data and sample data, the standard deviation and variance are different. Again, for population data, we divide by big N, that is population size. And for sample data, we divide by sample size minus 1, which is degrees of freedom. Okay, and there is a difference in notation as well. So for population standard deviation, we use the Greek letter sigma, small letter sigma. I know the big letter sigma is for summation, like sigma x. This is also sigma, but it's the capital Greek letter. Whereas this letter here, the small Greek letter, is for standard deviation. Whereas we use S for sample standard deviation. So we'll cover that again and remind you about this again in the next few slides when we talk about the difference between population variance and sample variance. And oh, one more thing before I forget. If I just divide sum of squares by n, it's population variance. If I wanted population standard deviation, I would square root sum of squares. Don't forget that. So here, and the same applies for sample standard deviation. Again, we use n minus 1 for sample standard deviation or sample variance, depending on what we're looking at. Again, remember, the standard deviation is the square root of the variance. So the next few slides here, part 1, 2, and 3, is going to be the story version of how we get the standard deviation. It involves a few steps. Step 1, 2, which is going to be changed, and then step 3, which is averaging the squared deviations, which gives us variance. And we're going to use population variance in this case, finally, with a step 4, which helps us get the standard deviation, which, if you're reading pretty fast, you can see that standard deviation here means the mean deviation or the expected deviation. So here we go. The next 3 slides then, which is the story of how or why we need to do certain steps, these 4 steps to get the standard deviation, so then we can start measuring variability in terms of referencing each score from the mean. So step 1. Again, we're not using range, we're not using the maximum and minimum, so we need a reference point, and we're going to use the mean for this. And because, just like we need to add all the scores to include everybody that we asked and measured, we also need to include all the scores in reference to the mean if we want to know how large or small the spread is. Therefore, what we're doing for each score is to calculate a deviation score. For example, if I had a score of 1, 2, and 3, again, let's keep this simple. We know the mean, we calculated before, 1 plus 2 plus 3, well, that's divided by 3, because, there are 3 people. 6 divided by 3, that's 2. Cool. Okay. So instead of using any one of these values, which is not the mean, these are just raw scores, even though the mean here is exactly the same as one of these raw scores, we calculated this. We're going to use the mean. And so what we're going to do is, well, I'm going to look at these values. I'm going to call this x1, x2, and x3. And you probably were thinking A, B, C, but anyway, I'm going to use these ones, x1, x2, and x3. Okay, so, and then the mean is also x bar. That works too. So if you see population mean here, I can do that. So I'm just going to change that for a second. Let's say our population is really small and is just mu. So a small population of 3 then with a mean of 2. And the scores are 1, 2, and 3. And I've kept the distribution real small, so then we can see step 2 very quickly. So our first step then, and there's only one of these, so 2, 1. Okay, next step. And we know the mean, so I'm just going to go x minus mu here. So our next step, well, okay, let's add up those deviation scores. And let's not forget, let's do that first. So x minus mu, x minus 2, well, that's 1. 2 minus 2, well, that's 0. 1 minus 2, don't forget, we got to do our negative signs. So here we got -1. And if you know the part of adding up, you already know what's happening here, either just by doing arithmetic or looking at the slides. You know what's going to happen. And that is, if I do my summation here, it's going to cancel out to 0. This happens at every distribution once you include every score and you subtract every score by the mean once. It's a guarantee. Again, I invite you to try this with any distribution that we have encountered so far. It doesn't matter if it's symmetrical, positively skewed, negatively skewed, bimodal, it doesn't matter. When we subtract a score from the mean, and we do this for every score and get a deviation score, and we do simple addition to get the mean as we are familiar with, that's not going to be enough, because the positive deviation scores are going to cancel out the negative deviation scores. So we have a problem, and we need a new strategy to deal with this problem where, okay, well, I can't do very much now. 0 over anything is 0, but that's not the spread. Here the range is 2, 3 minus 1, and the scores just by looking at it. They're 1 apart from each other, and even just looking at the data, and the mean. Well, yeah, one scores 1 up and one scores 1 down. So 3 is 1 larger than 2, and 1 is 1 less than 2. So 0 isn't the right answer. We need something else. We need something else. And the strategy is, instead of just getting deviation scores and getting the signs included, we want this, the absolute value. And to get the absolute value, we need to first square the scores and then square root it. The squaring cancels out the negative sign, or if you have 2 negatives, negative times negative is going to be positive. And square root, you can only square root big mistake. You can only square root positive numbers. You can't square root negative numbers. And so, you're going to end up with a positive number no matter what. So we want positive deviation scores, and we only want the distance. We don't want the sign. We just want the distance. And so that's what we're going to do. Which leads to a revised step 2. We're going to remove the negative deviations by getting this. which, as we discussed, is squaring the deviation scores, which you use for sum of squares. And then you're going to square root it later on. So this is the process we want. One thing to note here is that if you're thinking, oh, why don't I just square root the sum of squares first and then just get my absolute value and divide it by n? Well, that doesn't really work, because to get to this step, we must square the values first. So if we squared the values first, we must do the average or the expected value at the first stage and not at the second stage. So that means we need to do the variance first. We can't skip a step. So first we square the deviations. And let's try this again. Now we know from our frequency distribution, which is very small. Okay. Now we're going to work with this first. We need 2 more columns here. Okay, so here we go. Again, 3 minus 2. Oh, doesn't help if I write the same number again. 1, 2 minus 2, 0. 1 minus 2, negative 1. Well, if I square these, 1 squared is 1, 0 squared is still 0. Negative 1 squared now becomes 1. And so we add these up, and our sum of squares here is 2. Okay, so now we don't have a 0 anymore. As we know, if we just add 1, if we just add the deviation scores, we get 0 every time, guaranteed. So now that we have a sum of squares, again, remember, we can't skip a step. We got to do our average first. We have to average the square deviations first. And that's what we call variance. And so here, the population variance, we're using population parameters for now, whereas we're pretending or assuming that the small distribution of 3 for this presentation's purpose is population. So we use big N. In this case, then, we're looking for the mean square deviation distance of scores away from the population mean. And so this concept is going to be key in a few areas. 1, this chapter, obviously. 2, z-scores, which is coming up in chapter 5, where we talk about standardized score, which will help you bridge the connection between this chapter and the next chapter. Standard here being the mean, being the expected. And so we want to convert the scores into standardized scores or z-scores. We're going to use that as well. And finally, another area besides hypothesis testing, standard error, and so on, is going to be ANOVA, analysis of variance, because we're going to use variance as our foundation. So again, if you struggle with your sum of squares and variance and standard deviation by extension in this chapter, and don't deal with it, make sure you can tell the story to yourself and to others, and practicing questions in your textbook and other resources, and gauging yourself with either self-test practice questions or your practice quiz and so on. You're going to struggle in a few areas, like the next chapter, chapter 5, or in your future chapters like 6, 7, 8, and so on, that deals with variance and standard deviations, and especially ANOVA, where we analyze variance for groups of distributions. So keep that in mind as well. But I digress. So that's how we get variance, the expected or the mean squared deviation scores. And again, we use sum of squares because we want to deal with or remove the negative deviations, which cancels out the positive ones, which would give us a 0 sum of deviation scores, and it will always be 0. So we need sum of squares. So in our case, what's our variance for our small population of 3 people? Well, we calculated the sum of squares as 2, and so our variance here denoted as sigma squared, is the sum of squares divided by n, because we're dealing with population. And so it's 2 minus, well, 3, which is 1.5. Cool. Okay, now this will lead to our fourth step, because remember, two things. One, we can't skip a step. We need to find the average first once we square the values, or the square deviation scores. And because we're dealing with sum of squares, and so we squared the deviation scores, the scores we're working with, including the mean, are squared too. Which, if you think about it, is another reason why we can't skip a step. Because the mean we use to get the deviation has been squared already. We must square root it first. We must work with the variance first and then square root everything. Okay. So this is our last step, step 4. Once we've calculated our variance, we want to convert our sum of squares value back to our quote-unquote regular standard deviation scores. And to do this, it's fairly simple. We just square root the variance. So in our case, we got a sum of squares that is 2. We have a sigma squared of 1.5. Well, how do we get that? We got this from sum of squares over n, which was 2 over 3. We had 3 people. And that was... No. Excuse me. 2 divided by 3. That's not 1.5. That's not even 1.5 at all. It's actually 0.666. 1.5 would be 3 over 2. My mistake. Good teaching moment there. Always check your work. Okay, so, well, 0.666, which is important. We're going to need this for our standard deviation. Okay, so, sigma here, again, I stand corrected. I correct myself. 0.6, repeating. Okay, 2/3. All right, so we square root that value to get square root of 2/3. So for now, I'm just going to write square root of 0.6, repeating. So that would be our expected standard deviation score. And I, again, would strongly recommend that you try this with other distributions that we've worked with. And in the next slide, we're going to try it right now. Before we do this, let's cover the points again. Besides my miscalculation of 2 divided by 3, which I apologize, and going right into the steps, remember, we need the deviation scores first. Then we need to square the deviation scores for each one, then add them up as sum of squares, then divide it by n for population, or n minus 1 for sample, and then square root the variance to get standard deviation. So these are our steps right here that we need to do. And so let's give it a try then. In this one, again, we have some values. We got 5 scores, 2, 3, 4, and 5. And our frequency distribution would look something like this. Since there's only one of them, I'm not going to write the F for this one. So there's a 9, there's an 8, and I'm going to skip some values. 2, and there's a 5, and then there's a 1. Okay, so, and the mean here, and we can check this first. So 1 plus 5 plus 7 plus 8 plus 9. Well, that is 30. I got 1 plus 9. 1 plus 9, that's 10. 7 plus 8, that's 15. That's 25 plus 5, that's 30. Cool. Divided by 5, that's 6. So that works out. So the mean here is indeed 6. All right, so then we go first thing, deviation scores, which we need to, work with to get our square deviations. So our first one is 9 minus 6, well, that's 3. 8 minus 6, that's 2. 7 minus 6, that's 1. 5 minus 6, that's -1. 1 minus 6, well, that's -5. Again, if we add all these up, you got 3 plus 2 plus 1, that's 6, plus -6 plus -1 plus -5, well, that's going to be 0. That's not going to work. So we need to square those values. So here we got 3 squared, which is 9. 2 squared, which is 4. 1 squared, which is 1. -1 squared, which is 1. -5 squared, which is 25. Cool. Okay, so our sum of squares, I could write sigma and then x minus mu in brackets all squared. I'm just going to write sum of squares. Here we got 10 plus 25, that's 35, and then plus 5, that's 40. So we calculate our sum of squares. Let me double check one more time. 9 plus 4 is 13, plus 1 is 14, plus 1 is 15. Okay, 15 plus 25, that's 40. So far, so good. Now let me be careful with my next step. All right, so sigma squared. Sigma squared, sum of squares over n, because we're using population. Here's the mu, which tells us that. Okay, 40 divided by 5. Oh, phew, much easier. No mistake here. 8. So our sigma squared is 8, and that's our variance. And one last step, sigma, which is square root sigma squared, which is square root of 8, which you can write as a radical 2 root 2. So there you go. That's our standard deviation. So our scores in terms of standard deviations would be 2 root 2 from the mean. So that would be somewhere along here like this. Actually, root 2 is 1.41. So that would be somewhere around 2 times 1.41. So that would be somewhere around here. And then so that's one standard deviation. And then this is another standard deviation. And then that's just another standard deviation over here, somewhere like this. And so with the standard deviation, now you can start measuring how far your scores are away from the mean with a constant interval. Think of the standard deviation in a way as a ruler that tells you an interval that you can measure your other scores against the mean. So again, let's review the population variance formula. You're going to need the sum of squares and then divide that by the number of scores. So it would read something like this. Again, for population, it would be big N. For sample, it would be n minus 1. Okay. And then, so the sum of squares, if you remember, is based on the square deviation scores. And deviation score, by definition, is the distance of each score away from the mean. And so, what we have just covered is the definition of sum of squares with which we get variance and standard deviation. And that's one of the formulas we use to calculate sum of squares, the definitional formula. So this is the first one. Now, if you're wondering what the computational formula is and what it's for, the computational formula is a mathematically derived way using algebra, starting with this, of course. Again, this is our foundation. To go, okay, instead of doing deviation scores each time and squaring that and then adding those up, which would be quite time consuming if you're doing this by hand and you got maybe, I don't know, 20, 30, 40 people or scores that you got to work with. So notice here in your computational formula that you don't need to do any deviation scores per se. You just need 3 values. Well, actually 2. You only need the sample or population size in this case. We're working with populations for now, keeping our formula simple. And then we just need x's, but we need to do x squared. Just square the scores that you got, which is simpler. And then you add up all the scores and square everything. Or square the whole sigma x. So that's what the outline says. The definitional formula we've already talked about. You find the deviation score. Cool. You square each deviation, which cancels out the negative deviation scores, which would make the whole thing 0. Or the sum of deviation scores. So you do sum of squares instead. And then you get your sum of squares. In your computational formula, you square each score and then add those up. Then you add up all the scores and square the sum and then divide it by n. Notice this divided by n, because we're using mu for population mean, is derived from that. Well, we need to still divide by the population size in this case to get the mean. And so this is part of the formula. So again, we need to take account for population size. Again, there are proofs for this. And there are a few ways to find the proofs. One, you can figure it out yourself using algebra. Or Google some of the possible proofs for it. When I say possible, there's only really one. But people have different ways of writing the proof. Some more complex, some more simple. But it does involve a number of steps. Again, the advantage for the definitional formula is if you use the definitional formula, you know the story. And for most of our distributions, they're quite small in terms of the number of scores. It's no more than 20 scores, and you still need to calculate the mean anyway. So, it's always a good move. The computational formula is good in terms of for large distributions with lots of scores. And it's also a good way to double check your work. If, for example, you worked on the definitional formula and got one sum of squares, and then you used the same numbers and computed it with the computational formula and gotten the same number, then you know for double sure, because you double checked, that you got the right sum of squares. Well, at least you're more likely to get it, unless you've done it wrong both times. If you happen to get a different value for your computational formula, either by getting either formula wrong or having some mistake somewhere, then you got to double check your work. So that's a practical tip there when you're calculating the sum of squares. In this slide, we talk about some ways you got to be careful with the sum of squares. And this is especially true if we use computational formula because it involves more sigma notations. So review here for sigma notations. The sum of squares is not just squaring the scores. Again, the squares here is squared deviation scores, not squared raw scores. So squared deviation scores, yes, but not squared raw scores. No. Is also not adding up all the scores and squaring them. No. And one more thing, the two mistakes there, and actually those are part of your computational formula anyway. Sigma x squared, the first one, when you add up squared raw scores, that's not the same as squaring square the sum of scores, which is the second thing here. Sum of, not squares, scores. So these are not the same either. So again, watch out for those. So often what I've seen, this is a little tip, I guess, when I see students use the computational formula and only use the computational formula, especially later on in the course, which indicates that they've been struggling with this concept, they're likely to get it wrong. If I had 9 students doing it, 10 students doing that, 9 of them would get them wrong. It's because of mistakes like sigma notation. They didn't get that, or they missed parts of it, like divided by n, or they missed out on your sigma x squared and then sigma x all squared. That would be the first part. That would make a lot of students make mistakes if you use the computational formula. It also shows that they might not understand a definition. So again, which is why I recommend do the definition, repeat to yourself the story, write down that story, work out problems using the definitional formula, and then go from there. Use the computational formula as a check and as a more speedy way once and only after you have mastered the definitional formula and the story. Okay, so here are some notations for the population variance formula. Again, it's big N because we're dealing with population, not n minus 1. That's another area where students lose marks because they use the population variance for sample data or use sample variance for population data, which happens when either late in the course and you're doing the final exam and you didn't read the part, do population variance, I use n minus 1 because I use it all the time, or I use population variance for a sample question, because I've been working hard the first part of the semester and then I forgot, I need to use degrees of freedom for sample data and so on. So make sure you pay attention there. So notation is important. Make sure you know whether you're dealing with population or sample, which is why the first chapter we really help make sure you differentiate between population and sample. Here though, notice again with population and parameters, population data, we use Greek letters. Variance, we use sigma squared, small letter sigma, or lowercase, I should say. And standard deviation, we use sigma, lowercase Greek letter sigma. So our first learning check then of the chapter. 2-part true and false, or true or false. It's dichotomous variable. You can't have either. You can't have both of them. Anyway, A, the computational and definitional formulas for sum of squares. What the? Oh, right. It's underlined. There you go. Sum of squares sometimes give different results. True or false? And B, if all the scores in the data are the same, the standard deviation is equal to 1. Well, take a moment and think about this, especially for B, and also A in a way, because we just talked about it. And what do you think? Again, review the definition for sum of squares and think about what happens if the data is all the same scores, and check. If you answer false to the first one, you're right. Remember, especially if you have tried to derive the proof for the computational formula for yourself, it is an algebraic rearrangement. So then we no longer have to deal with deviation scores, but you still have the minus, which accounts for deviation, and you add them all up, and it should give you the same result, which we talked about. And again, there are ways to use it which will help you. Again, if you get the same result for both, you've probably done it right. For B, it would be 0. All the scores are the same. This is one line. And so you would have no standard deviation because all the scores are the same. So that's the logical explanation. And again, if you want to try it, the sum of squares would be 0 anyway. So if the sum of squares is 0, then 0 over anything is 0, no matter how large the sample is. Okay, question 2 is a multiple choice this time. The standard deviation measures what? And you have 4 choices. A, the sum of square deviation scores. The standard distance, that B is the standard distance of a score from the mean. C, the average deviation of a score from the mean. Or D, the average square distance of a score from the mean. Again, for this one, think about the nature of standard deviation and variance. Think about whether they're the same or different. And think about how they're related to each other. What is the standard deviation? If you answered B, you're right. Remember the sum of square deviation scores? That's the definition for sum of squares. The average deviation score from the mean? Doesn't really happen actually. Remember, if you just add up all the deviation scores, the positives would cancel out the negatives, or the negatives would cancel out the positives, whichever way you look at it. And so it will be 0. For D, the average square distance score from the mean, that's actually a variance. And so the standard distance here, again, there's 2 ways for you to think of this. If you just thought, oh, standard, that matches, if you're doing this in a test, you might get away with it in terms of just a lucky break. But really, standard here means the average. And the distance of a score from the mean, well, that's derived by the square distance. So that's the more technical, and that's a more precise way of saying, well, what does the standard deviation measure? So that's it for our first part. And so remember what we said. In this slide, we're looking at sample data. So I'm going to give us a break here. And so again, we've done at least the first 3 steps. We have explained and described measures of variability, about the range and its limitations, and we described the story of how we get the standard deviation as a more consistent, more reliable, and the most common way of measuring variability by looking at the sum of squares, which we need because we want to deal with negative deviation scores. And then we get deviance by finding the average sum of squares, and then we square root that to get standard deviation. So now that we've done it with population data, not sample data, we're going to address it with sample data as well, and then go from there and basically finish our chapter for the day. And so yeah, again, no substitute from working with the textbook or practice questions. Again, the textbook has these concepts in detail. It has more practice questions for you to do. Our modules do have practice questions which you can do with our with using Microsoft Edge or Google Chrome, and I'm going to show you this real quick. Your formula sheet again is right here, which you would use. Again, we're using sum of squares, variance, and standard deviation. And again, with these modules, our web tutorials, again, if you use Chrome, it's not going to work because Chrome has disabled Flash. And if you know a way to enable Flash on Chrome, let me know. But if you use Firefox or Microsoft Edge, or if you're an Apple user, use Safari, should work. So let's try it with Firefox, for example. Okay, I'm just going to open the Microsoft Edge one just in case. No, Firefox doesn't work. Well, for Windows, you have Microsoft Edge anyway. So, no, I'm sticking with Chrome. And allow. And once you allow it, you can work out these problems right here. So that's one resource. There you go. Again, you'll be asked to calculate sum of squares, and then you can do this. Remember, to get sum of squares, you need the mean first. So again, our reference point is the mean. So you can try the resources there. You can go to your textbook. You can get practice questions. And that is really the sure way for you to really get a grasp on this chapter and practice the questions. And in our test, that's what we're going to test you on. So again, make sure you stay on top of things. If you got any questions after you check your textbook and other resources, and even going back to these videos to review, you can pause, skip, whatever, and ask me via email if you got direct questions after checking out the resources. You can do it. So until part 2, we'll see you in the next one.